The solar system is large and old. Using half-life decay measurements on asteroids that have fallen to Earth, many astronomers have been able to tack on a number of about 4.5 billion years to our solar system. By our current understanding of the age of the universe, that's just about a third of the time that, well, anything has existed at all. It makes sense then that as creatures of curiosity, we would very much want to learn how such an entity came to be. The first theories on how our solar system formed came about before anyone was aware that any other solar systems existed, before the Sun was found to be made of similar elements as the Earth, or heck, even before all the planets of our solar system had even been discovered. Nearly 150 years before William Herschel proposed that Uranus might be a planet rather than a star or a comet, René Descartes in the early 1630s had written in his book titled The World on the possible origins of the solar system. As Descartes wrote, it was the swirling of matter in vortexes that brought about the Sun and the planets, thus also explaining their circular orbits. However, concerned for persecution similar to what the Church had done to Galileo, Descartes withheld the book, and it wasn't published until his death. 100 years afterwards, Immanuel Kant published a book titled Universal Natural History and Theory of the Heavens, which upheld a similar theory in that the galaxy was a rotating body of stars, and that the solar system represented a smaller model of the galaxy. He also similarly posited that such spinning structures may have formed from gaseous nebula. This forms the basis of the solar system nebula theory, and despite various problems found with it throughout the next few centuries, it would come to be the generally accepted theory of solar system formation. In short, it says that large masses of interstellar gas will gravitationally contract, possibly spinning and forming a protoplanetary disk. From here, most of the gas and dust will concentrate at the center, possibly reaching a critical mass to begin fusion and become a star. The rest of the rotating disk will then coalesce into planets and asteroids, while any remaining debris will be blown by solar radiation beyond the reaches of the solar system. Current simulations of solar system formation seek to recreate the mass of contracting gas and dust through what's called n-body simulations. These attempt to model interactions between a large amount of discrete particles over time. The simulation is divided into time steps, where one time step equates to one cycle of calculations, after which the locations of each body is noted and another step begins. Various initial conditions may be modified, such as how many particles initially exist, or how large will the time step be. Different forces can also be accounted for. For example, while gravity is a predominant force in these simulations, would drastic differences be observed if accounting for the push of solar radiation coming from the star? Another example, for those interested in the water composition of planets, is the location of what's called frost lines, which are theoretical divisions beyond which various volatile compounds will freeze. After these simulations have run their course, we would then be able to glean from them trends, flaws in current models, or observations of simulated phenomena which may even warrant further study. Now, the issue with these simulations is the uncertainty around them. From the simulations themselves, it becomes quite clear that limits on computational power will restrict the accuracy of the simulations that can be practically completed. Relevant to this is what's called the n-body problem, in which as more individual bodies are added to an n-body simulation, the task of calculating the simultaneous interaction of each body upon each other becomes much more complex. Here, observing the difference between a two-body system and a 10-body system, it should become apparent how this might become an issue. The most glaring source of uncertainty, however, stems from the fact that the process of forming planets takes time, many orders of magnitude longer than a human's lifespan. This means that many of these simulations are only testable by comparing them to various stages of planet formation observable in foreign star systems. Otherwise, the process of observing a solar system coalesce in real time would take much longer than the human race has existed for, an obviously impractical endeavor. Because of this, our model of planet formation could very much change based on things we have yet to observe, as our astronomical tools become more and more powerful. For example, it has been noted how recent missions to Kuiper Belt objects may have an impact in how violent the process of our solar system's formation may have been. However, this is very much still a developing science, and one that may hold great significance in various astronomical fields. In the search of life, we may improve our understanding of what conditions may provide for Earth-like planets, And overall, bettering our understanding of our solar system is one step towards bettering our understanding of the universe. Thank you for watching.